Well, good morning, HASS members. Welcome. It's nice to see all you geology geeks here in one room. We're happy to have you here. I am Linda Fulton, and I'm a member of the Science, Medicine, and Technology Curriculum Committee. And our team is happy to bring you today's session. So you know the drill, so make sure that these are not making any extraneous noise so as not to distract from today's presentation. Thank you for doing that. And we want to welcome those of us joining via Zoom in the HASS virtual classroom. And special thanks to course technician Gloria Goodwin for supporting our hybrid modality. And if you have questions or comments at any time, please raise your hand and we will get you a microphone so that everybody can hear the question. So today we have a double feature. We are happy to welcome Jon Peterson of the Hope faculty, and he's going to do a deep dive into the geological history of our state, which will help us understand how geology has shaped our beautifully scenic state. Jon has been a member of the Hope College faculty since 1994 in the geology/environmental science department. He received his bachelor's degree from Hope College and a doctorate from the University of Chicago. He has also worked for Amoco in Houston and Chicago. And just a few other bits of trivia. He plays trombone in the Hope College concert band. If you were there at the musical showcase, he was in his chair playing trombone. And he would like to mention that he is also a Muskegon Big Red, if there are any of you. I knew there would be at least one or two. Okay, well, that's the end of the introduction. So, Jon, let's rock and roll.
Hey, I like that. So thank you. Thank you so much for inviting me. It's always our pleasure to talk about geology and to talk about Michigan. And let me start out by saying we're going to do a travelogue type of approach here. We're going to travel from the oldest rocks to the youngest geologic materials in Michigan. And I hope you don't mind traveling because we have to travel quite a bit around Michigan. But I want to start out with this man, Douglas Houghton, for several reasons. Geology is done by geologists. And Douglas Houghton is a good example of the field of geology. Field of geology is very broad, very interdisciplinary. It also spans big scales, planetary scales, to putting atoms into crystals. So I just want to start with a little call out about Douglas Houghton. He was the first state geologist of Michigan. He was truly a Renaissance man. He was a practicing physician in Detroit. He led the Schoolcraft expedition to Lake Superior. He was the first professor of chemistry at the University of Michigan. He was founder of the American Academy for the Advancement of Science. He was the mayor of Detroit. So I would say he was slightly an overachiever. And he drowned off Eagle River, Michigan. And you can see he was he was about 36 years old. All right. An amazing human being. So just a call out to Douglas Houghton. Here's where we're going to start. We're going to start with a map. And this is a geologic map of Michigan. Now you might say, I've never seen a map like that. It looks very strange. Well, this is the bedrock. Okay. This represents the consolidated material that is forming the bedrock of Michigan. And we have a lot of different colors here, which is typical of geologic maps. And we have geologic ages over here. You may recognize some of these: Jurassic, Devonian, Silurian. We're going to go through all of these. Now, just a little heads up, you're going to see this a lot, okay, today, this map, because we always want to go back to the map and see what, in fact, we're looking at. Now, a little piece of information you can take with you is on geologic maps, the further down the column, the older the rocks, and at the top, the younger the rocks. You'll always see that on geologic maps. Whatever map you're looking at, whatever part of the world, the younger material will be at the top and the older at the bottom. All right. So let's take a quick overview now of the Precambrian. This is old stuff, okay? So if you look up here, this is 4.6 billion to 543 million year old rocks, okay? And they are shaded right here in Western UP. Now, it's really important that we get a sense for a billion, okay? A billion is 32 years worth of seconds. So 1 billion is 32 years worth of seconds. So that gives you a sense for how big that is. Now, anytime you see the word billion, you know now, wow, that's a big number. Trillion, really big number. National debt, we won't go there. Okay, so we're going to be looking at the Precambrian, and we're going to start over here in Watersmeet, Michigan. Watersmeet, Michigan, the rocks, they're the oldest rocks in Michigan, 3.5 billion years old, or 3,560 million years old. Now, what do those rocks look like? This is what they look like in the field. There's a rod, a pry rod for scale. And this is called an Archean gneiss. And it's about 3,500 million years old. And you look at it and you say, wow, that looks like it's been through the mill. And it has. It has gone through a lot. When we look at rocks, we always want to try to figure out what was the protolith. And the protolith is the rock before the rock, or the material before the rock. This is a metamorphic rock. Over its multi-billion year history, it's been squeezed and heated and deformed, and you can see how it has a linear pattern to it. Well, before this was heated and squeezed, it was a lava flow, all right? And we know that because of the chemical composition of this rock. What was the Earth like back then? It was not a very hospitable place for life, all right? So it was a very hot, dynamic planet at that time. There were multiple lava flows that were erupting, forming a very preliminary crust or surface that got digested over and over and over again. But at some point, we started to solidify a crust and started to get a permanent terrestrial substrate on the planet. Now, I'm going to continue to say an aside because my asides are general things you want to keep in mind when you think about geology. The Earth has been trying to cool off for about 4.6 billion years. That's essentially the driving mechanism for all of this. Okay? We know from thermodynamics that heat always flows from the hot body to the cold body. So planet Earth has been trying to reach space temperatures for 4.6 billion years. So all of this activity is heat driving this. Heat from the center of the planet, heat from radioactive decay, etc. All right. Now, we are talking Watersmeet. We're talking down here in this column. This is a different column, but down here in the Archean, that's what we call this. And this would be, you know, early to mid Archean. That's where we are in the column. Now, throughout the day, we're going to go up this column. All right. How do we know those rocks are so old? I mean, that's the question, right? Everybody thinks, well, how do we know they're old? The best way to think of this is like an hourglass, okay? We know an hourglass, we have sand in the top and it drains down to the bottom. The relative amount of sand up in the top compared to the bottom is a function of what? It's a function of time. Yeah. So the more time that's passed, the less will be at the top and the more will be at the bottom. this is really the principle we have to think of with radiometric dating. Okay, this is a mineral called a zircon. It's zirconium silicate. And these little zircons exist in these old rocks. And they have uranium in them, and they have lead in them. And so if we know the relative amount of uranium compared to lead, they're called parent to daughter, and we know the rate, then we can figure out how long that rock has been doing this hourglass, okay? Now, uranium lead is just one pair of elements. We have other pairs that do the same thing at different rates. So oftentimes, usually when we date rocks or do radiometric dating, we use multiple pairs to get to these dates. All right. Well, we're at Watersmeet. We're going to take a drive now. We're going to head northeast. You know, those UP roads can be either really beautiful or really not beautiful, depending on what time of year. Okay, well, this time of year, we're going to go in the fall, okay? Don't worry, spring's coming, okay? I'm not turning the clock back. We don't have to go through, you know, the winter again. But here we are driving along the UP. And we're going to get up to the shore of Lake Superior. And look out, okay? When you pass through the area around Champion, Michigan, and near Van Riper State Park, maybe some people have camped at Van Riper, you do have to look out for these, okay? That is a mess if you hit that. So let's get up to Marquette. Now you notice here with Marquette, we have gotten to younger rocks now, 2.6 billion year old rocks, starting from here up to here, okay? So we've covered, you know, about 1 billion years now of Earth history. And this is a little bit of a complicated map, but what I want to show you there is that right along 41 up there that comes through, I'm sorry, 20, oh, sorry, I think it's 26 comes through, Ishpeming, we have rocks to the south that are granites and rocks to the north that are volcanic basalts, okay? And so we have two main types of rocks, one north of the highway, one south of the highway. And these rocks to the north in Marquette area are called greenstones. They are metamorphosed lavas. They are lavas that, just like the rock we saw at Watersmeet, have been changed due to heat and pressure. All right. They probably looked like this when they were erupting. This rock type is called basalt. Basalt is the most common rock on the planet. So if, let's say, you were chosen to go to some distant planet and you were going to meet with the people there, and you were allowed to bring one sample of rock that would represent Earth. Okay, this is highly fictitious, obviously. Bring a basalt, okay? Because the basalt, the majority of our planet is basaltic in composition, okay? This has high magnesium, high iron, and generates these types of lavas. The oceanic crust of the Earth is basaltic. All right, so this is what it probably looked like. Well, this is what it looks like in outcrop along US 41 near Marquette. Now, what's so special about these? These are called pillow basalts. I don't know if you can see the demarcations in here. I'm going to outline a pillow. Pillow comes like this. There's one here, like this. And we see things like this, okay? The scale here, this is probably 18 inches across right here. If you want to go see these are right to the as you come into the Suzuki Yamaha outdoor vehicle shop on the north side of the road there, right outside of Marquette. They're kind of back there, and there's probably some junk parked around it, but there they are. Now, what's so important about these? What's so important about these is that they represent basalts that were erupted into seawater. Now, how do we know that? We know that because some crazy geologists put on scuba gear and filmed basalts in Hawaii being pushed into the ocean and forming these pillows. All right. So a very important principle in geology is that the present is the key to the past. So what we see today, if we have no other reason, we will interpret what we see happening today as have happened in the past, right? So what's so important about this? These are called chill margins. And when that basalt comes in and chills in the seawater and sinks down to the bottom, and they stack on top of each other. The obvious but incredibly profound conclusion is there was liquid seawater on the planet at this time. And we know that from observing the formation of these pillow basalts. Now, this region also has some valuable things in it, like gold. It's been gold mining up in that region in these greenstone terrains, as they're called. They've been productive around the world for gold. Much of the Canadian gold mining is based on these greenstones as well. All right, we're going to move a little bit. We were here. We're going to move now into a time period called the Proterozoic. I'm going to get a little younger. There's where we were. We're going to drive south on 95. You can see this. Some of you may have taken that road. It heads south 95, goes down to Crystal Falls, Menominee, etc. The roads look like this, right? Anyone who's been in the UP this October and sometimes late September, beautiful. We're going to look at rocks now that are called banded iron formations. BIFs in geologic circles. Maybe some of you have seen this. Maybe some of you have seen these. Ishpeming, Michigan, Negaunee, Michigan. These are banded iron formations that were formed about 1.8 billion years ago. And they were also metamorphosed. Okay, when we get to these old rocks, they've all been metamorphosed. They've all been squeezed. They've all been heated, all been changed in their appearance and structure. Now, this is very beautiful. The red is jasper, and the gray is hematite and magnetite. Those are iron oxides, and jasper is a silica mineral, all right? Now, what is so important about these banded iron formations? Well, we know there's been water on the planet, seawater on the planet. Now we're, 900 million, 800 million years later, and we have these iron-rich sediments that have been squeezed into these iron formations. Here's the dilemma. The dilemma is the solubility of iron is not that high in seawater right now. In other words, you can't put that much iron into seawater. But back then, we had a lot of iron in seawater. The reason we had a lot of iron in seawater is because the atmosphere was much different. It was a much more CO2-rich atmosphere, which allowed more iron to dissolve in the seawater. That's the only way we could have this concentration of iron settling out of the ocean to the ocean floor. Okay, so Earth is dynamic, always changing, always changing. All right, now, this has proven to be extremely important economically for the state of Michigan and the country. We have the Iron Ranges, as you see here. We have the Marquette Range right here. It's got two arms on it, this one and the Republic Range right here. We have the Menominee Range, eastern and western Menominee Range, and the Gogebic Range. This is a source of iron ore, has been a source of iron ore. And without iron, you can't make steel. And without steel, you can't have a modern society. So Michigan has played a huge role in the advancement of our country for sure. We're going to go down, like I said, to Republic, Michigan right now. And as I was saying, the iron industry, the iron boom, a very important part of the geologic history of Michigan. I am told, and I believe it, that there were things called iron dollars. Is anybody familiar with iron dollars? Cleveland Cliffs Mining Company. People probably heard of Cleveland Cliffs before. Cleveland Cliffs would, totally illegal, they would print money, okay? Because it was so hard in the winter to get cash up to the UP that what they did is they would print dollars. They were called iron dollars. So the workers would be paid in iron dollars. They could do commerce around town. They could buy groceries, do things like that with this funny money, these iron dollars. Then in the spring, when the snow melted and the ships would come in, it would get exchanged into US dollars. And I've seen a couple of these iron dollars in the museum up there, but it's fascinating, isn't it? That certainly wasn't legal, but they did it. Okay, so that iron ore, you can see the red color. The banded iron formation gets pounded into taconite pellets. Like that, there's a quarter for scale. This is the Republic mine, or I should say the Republic mine before it was flooded, all right? And it's an open pit mine, and a lot of iron ore has come out of the Republic pit. Now, just an aside, with mining, water is always the issue. Moving water. And moving water is expensive. So you will see these open pit mines, if they are closed, they're flooded because they stop pumping the water out, all right? And we look at this open pit mine, we say, wow, that's really an eyesore. It is. There's been a lot of reclamation up there where land has been reclaimed from mining. But there's an old adage in economic geology that goes like this. If you can't grow it, you've got to mine it or pump it. And think about it. There's something to think about with the extractive industries. If you can't grow it, you have to mine it or you have to pump it. And if you think about that for a while, you see that you'll see that that's actually true. All right, so let's load up our lake freighters, and with the taconite pellets, of course, we have to move them down to the steel mills in Ohio, northern Ohio. Okay, now we're going to take a little head northwest. Okay, so we're going to get on the highway again and head northwest up to the Keweenaw. Now, notice we are getting younger. We are getting younger in age. We're going to go up now to the middle and early Proterozoic time period right here. Remember, we're going up this geologic column. Another beautiful road. This is right outside of Baltic, Michigan. I don't know if anybody's ever been to Baltic, Michigan. Yeah. Beautiful area just south of Houghton. And we will pass outcrops along the road that have granitic rocks or granites like you see on your counters or in people's kitchen or on the stairs at Van Wylen Library. And we see, in fact, basalt, dark lavas, cutting across them, okay? Cutting across them, coming from deeper levels and moving up higher towards the surface. Wow, what is this? Well, what I'm showing you here is a geophysical map. And do you notice about the mid-continent, there's something that looks like a worm or a snake. Yeah, right in here, goes up like this, and then part of it comes down here like this, okay? Now, you don't know that's there unless you look at the subsurface or look at the outcrops. This is a rift system in the crust of the earth. It's called the Midcontinent Rift system. There's a better map of it, the Midcontinent Rift system. When we have things like an earthquake in Kalamazoo or something like that occasionally, it's due to reactivation of some fault along this rift system. All right. So this rift system has been there a long time, been there for about 1 billion years. So I guess we can say it belongs there, right? But so it starts out here in Iowa, comes up through Lake Superior, turns and comes down through the heart of Michigan. What's an analogy? An analogy is East Africa. The East African rift system today is very similar to what that one was in the mid-continent of the United States about 1 billion years ago. If you just look at this map, there's a lot of stuff on here, but what you see is there's what's called the East African Rift Valley, okay? And what's happening here is the plates that form the Earth's crust are actually pulling apart. They are moving in opposite directions and opening up this rift. Now, when you thin, you can imagine a crust, and if I pull it apart, what's going to happen in the center of it? It's going to thin. When you thin that out is when you get the volcanic eruptions coming up through that thinned crust, all right? And the activity would look something like this. Very bubbly basalt, lava flows coming out of fissures, long fissures, as this crust pulls apart. Now, here is a cross-section of what's happening in the Lake Superior region. So it's just like we're taking a cross-section, slicing the earth and looking at it sideways. So for bearing, there's the Keweenaw Peninsula, there's Isle Royale, Thunder Bay region. Here's a map down here. You see the wolf's head? We're going right through his eye, okay, like that, across the lake. And if you took that line and stood it up, it would look like this. So we have two faults that bound this area. One is the Keweenaw Fault, and one is the Isle Royale Fault. And we have this basin of rock material in between, all right? And this is that roughly 1 billion-year-old volcanic material that is so important in the Keweenaw. There is a map. If you've driven up into the Keweenaw lately, fantastic area, right? Fantastic area. You drive up 41, and on the east side is that's the part of the fault that's towards the east. Then you go towards the west, and you're in that trough or basin. It always is fascinating to me. I've never done this, but I'd like to do it someday, maybe in retirement. I'd like to start at Copper Harbor on US 41 and drive all the way down to the bottom of Florida. You can do it, you know? To think that that road ends in Copper Harbor is also Lakeshore Drive in Chicago. Lakeshore Drive is US 41. Go all the way down to the tip of Florida. I think that would be, has anybody done that? Maybe somebody's already done it. I don't know. All right. Well, here are those basalts in outcrop. We call that outcrop form when it pops out at the surface. And they look like that. Not that impressive, but boy, when you mine those, you find there is copper in them. And that's why it's called the copper country, right? Now, I got a few more pictures of copper. This copper was so special because it's native copper. So it's not in the form of sulfides or other forms of chemical compounds. It's native. All that had to be done was mine it and stamp it, and you had it. Okay, so there was no chemical processing required. This made it incredibly, incredibly economically valuable. And of course, if you've been up to the Seaman Museum at Michigan Tech, you see these beautiful museum specimens of copper that was formed in the spaces, the cracks, the holes in those basalts. All right. And the seawater came up through there and precipitated out this copper over many, 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 many years. Now, has anybody been to the Seaman Museum up in? Yes. Now, they've got fantastic specimens from all over the world. The reason that collection is so great is because of these native copper pieces. They traded around the world. They traded with the Smithsonian. They traded with other museums around the world to get some of those other minerals that are fantastic specimens. So this was really an asset for them to be able to trade these pieces. Some of you may have pieces like this. Fantastic stuff. Now, that was a huge economic boom up there in the Keweenaw. That's the Quincy head frame right there. You can take tours at Quincy. I've taken geology classes down into the mine at Quincy. I have a personal vested interest. My grandfather worked the Calumet Hecla mine in the UP. He was a Finnish immigrant who came over and spent his life in those mines. My mom is from Copper City, if anybody's from the UP. So, that was fashioned into ingots like this and used for all kinds of things, but mostly for the electrification of the US. The fact that copper wire was needed to electrify the US at this time. Now, I had mentioned to you that the native copper, as we call it, the elemental copper, was so valuable. There are other copper ores, right? And some of them are here, beautiful samples, bornite, chalcopyrite, other ones here. But these have to be processed. So they're copper sulfides, they're copper nitrides, they're copper chloride. You know, they have other things on them. So there would have to be a chemical process. And actually now we get most of our copper from the Western United States. And it's all mined as these other compounds, not as native copper. So the obvious question, why did we stop mining the native copper in the UP? I mentioned it a little while ago. It was water. There were other things. There were some labor issues and things like that. However, the mine's shafts got so deep that to pump the water out got too expensive. And it's much cheaper to open pit mine than it is to shaft mine. Okay. So it was just an economic reality tied in with certain labor constraints and things like that that really put those mines out of business. Okay, I'll tell you what, I'm going to just pause for a second. Questions right now? Any questions right now? Yeah.
Bring your microphone.
All right.
I think the colors would be richer if we turn the lights down.
Ah, well, maybe we can work that out.
With all the lava flows that you've been invoking, are there any evidence for the volcanoes where they came from?
So in the UP here?
Yeah.
They were a type of, yes, I mean, it's a great question. This is a type of eruption that's very similar to what we see in Iceland today. So they're not the big, high composite volcanoes like we think of in the Northwest, Pacific Northwest. but they're oozing fissures along the crust, much like Iceland. Okay, so not the big high stratovolcano. I'm glad you asked that question though, because that gives me a chance to talk about why. Why do we have some volcanoes that are high, big mountains, Mount Rainier, Mount St. Helens, Shasta, etc., and other ones that are cracks in the crust that just ooze out things? And Hawaii is another type of this. It has to do with the amount of silica in the lava, SiO2, okay? The amount of silica in the lava goes back to its chemical composition. Let me dig into that a little further. The more silica that's in the lava, in the magma, the stickier it is, the higher the viscosity. All right, you think of your oil in your car, 5W30, those are viscosity numbers, right? How easily does it flow, okay? So the viscosity increases, the stickiness increases as the silica content increases. As the silica content decreases, it gets much more fluid. So the basalts, the dark ones, low silica, they can flow easily. They can't form a large mountain. Mount St. Helens, Mount Rainier, etc., those are silica-rich lavas. They can hold together because they're much more resistant to flow. So they can build up a volcano. Now, one more thing. The stickier lavas, the stickier volcanoes are much more violent in their eruption than the basalt, easily flowing lavas. Why? Because the sticky ones can't degas. Think of breakfast, think of making oatmeal. You know, of course, why is it that we always burn the bottom of the pot, right? But that's just a human problem, I guess. But the point is, as that thing starts to boil, what happens? The gases, the air in that oatmeal goes, right? As those bubbles try to come out of that oatmeal, as opposed to something very fluid like water. You're boiling water, it just kind of roils like that. Same thing with lavas, okay? If a magma or a lava can't degas because it's too sticky, too much silica, too viscous, what happens is the pressure builds up in there and you get the massive explosions. So the basalts can degas very easily. They're not violent. They're hot, but they're not super violent, okay? Thanks, that's a long answer to a short question, but all right. Yes, sir.
You mentioned the existence of native copper and then other copper
Yes.
compounds.
Yes.
Like copper, silicate, and those kind of
Yeah.
things. Is there a simple answer to the question of why is some copper native or pure, I guess, and a bunch of it is not?
Yeah. But it's not simple, but it's a great question.
I can retract it.
No, don't retract it. But the pH, the oxygen levels were just right for that native copper not to find somebody else to bond with. It's a geochemical, a sweet spot. Yeah, okay, great. Anything else? Yeah.
Just
Yes.
a quick question. The rift in Michigan, how old was that rift
It's about 1 billion years old.
compared to the one in Ethiopia?
That's rifting right now.
Oh, so this one is much older? than
Much
the one-
older than Ethiopian. Yeah.
Really?
Oh, yes.
Oh, I didn't-
Yes, yeah. And we have active volcanic activity. I mean, there's in the East African Rift right now. Yeah.
As a person who lived for a long time in Wisconsin, we're having this boundary here where we see that this is the UP, but does some of these geological formations continue into Wisconsin?
Yes, they do. They do. They're part of, and I may have a slide in there. This is part of something called the Canadian Shield. And the Canadian Shield is a piece of ancient Precambrian crust, some of the first crust on the earth that formed, and it goes down into Wisconsin as well, dips down into Wisconsin. And when I say the Canadian Shield, this was the first bit of crust that didn't get recycled. As you remember, back in the early Earth, there was this constant recycling. We'd have these volcanic eruptions, and then the crust would get recycled and resorbed into the planet. So it's called the Canadian Shield. Yes, it does come down into Wisconsin as well, and Minnesota, all the way to the Minnesota River Valley. Yes.
That Lake Superior, the rift, how does that compare to the Niagara Escarpment? It looks like it's the same.
Well, we haven't gotten there yet. That's a great, we're going to get there. It's younger, a lot younger. Okay. Good. Yeah.
This is a little bit off the main path, but very early in the history of Hope College, like before 1880, the college was given a huge rock collection, and it's always mentioned in the histories of Hope College. I'm wondering if that was a significant rock, like an amateur collection of a little hobbyist, or whether that was some kind of fairly significant rock collection, because how much of this was known in before 1880? I mean, how far along was geological understanding, in that period for Hope to even start in that direction with science?
Yeah, it's a great question. I don't know. If I can rephrase it for myself here, what you're saying is, at what point of our understanding was that rock collection given to Hope?
Okay.
In fact, it may be more significant now recognized than then.
Oh, well, it was in the college's possession before 1880.
That's-
You see the campus maps, and there's one little telescope sticking up from something that looks like a chicken coop. So they were trying to look up in the sky. And I guess they had stopped adding up the begats in the Bible to learn the age of the earth. But if they were given a significant enough rock collection, and it was like what you're talking about, was the beginning of everything you're talking about, the time periods.
Right.
Already in Hope's possession by 1880.
Interesting thought. And yeah, by 1880, we weren't doing radioactive dating because we didn't know we had radioactivity yet. Oh, certainly by 1940. Radiometric dating started about 1912, very early on. There's a great history of science piece there. Radioactivity was discovered about 1898, Madame Curie and William Röntgen. And then, just to tell you that some lights burn brighter than others, Ernst Rutherford, the great physicist, after he had seen that, wow, there's this radioactive decay, this spontaneous decay, he said out of the blue, wow, I wonder if we could use this to date the earth, So, yeah, exactly. Okay, we better move. So here's our map again. Now, we were just there in the Proterozoic period, about 1 billion years old. Now we're going to go over to Munising and notice the change in age. I mean, we're really getting young now, right? 540 million years old. That's young stuff, right? So we're going to go across the lake. I hope nobody gets seasick. I said it was a travel log. I didn't say we'd be driving the whole time, right? As we know, anyone who's been on Lake Superior knows Lake Superior can be a wild ride for sure. All right. So now we're going to go into a period called the Phanerozoic. And I want to point out on this material here, this comes in these brackets here, okay? So you see 251 and 542. This comes down to this section right here. It's hard to put all of it on vertically. So we're going to come right into this area right here. And we are going to look at the Cambrian period, named after Cambria in England. A lot of these names come from the British Isles. There's a history of science, I suppose, two schools of thought. One school of thought is that essentially the British and the Scottish invented geology, and the other is that the Germans invented it. And I have no dog in this fight at all, okay? But a lot of these names come from the British Isles. Now, the Cambrian, all right. And you see this strip of rock that goes just like this through pictured rocks. Right there on our column. This is called the geologic column. Beautiful, beautiful pictured rocks. We know that many of us, I'm sure, have been there. There's sandstones. Sandstones being rocks that were at one point sands, loose, unconsolidated sand that has been compressed and lithified into a coherent material. Now, this is where we have to dig into this a little bit more, because I said to you, wait a second, we went from like 1 billion to 540 million. What happened? In Earth history, there are these fascinating things called unconformities. And unconformities are missing time. Now, we know that the clock has always kept moving. It's not really missing time, but it's a missing record of time. And they are called unconformities. And I'm going to explain this to you here on this diagram. So, if we have an ocean and this ocean is depositing sediment on the ocean floor, and let's say it deposits sediment 1, okay, that becomes a rock, and 2 and 3. So we're getting younger, 1 being the oldest here, 4 being the most recent. So we deposit these rocks on the ocean floor, 1, 2, 3, 4. And then we have sea level drop, and we expose these rocks. So this is underwater now. Sea level drops, and this is now subaerial, as we call it, and erosion takes place. All right. So erosion takes place, and we end up eroding away rocks 3 and 4. Okay, they are gone. They've been eroded. They're in streams, and they're going elsewhere. And then sea level rises again, and we start depositing material on top. And now we deposit 6 and 7. What happened to 3 and 4? Well, they're not there. It's missing time. It's called an unconformity. So when we study the rocks, if we study this, we say, oh, rocks 1, 2, 3, 4. We study this section, 1, 2, 6, 7. That's what's happening when we see these big jumps in time. We're talking about unconformities. Very, very fascinating piece of Earth history. All right. They don't just occur in, Munising. The Grand Canyon has a huge unconformity. Right here, you can see it. It's called an angular unconformity. Why? Because the rocks below are at an angle to the ones above. So here is missing time in the Grand Canyon. So these unconformities perplexed geologists for a long time, but got it figured out in Edinburgh, Scotland. All right, about 1789. Now, the sandstone, the Cambrian sandstone, is called the Jacobsville sandstone. It's named after Jacobsville, which is was up there on the in the UP, right on Lake Superior. And it looks like that. I like to call it bacon rock, just to put a little food sense to it. If you go to Calumet and you look around some of the towns in the UP, you'll see that it was used for building quite often. And this one up here is a very great example of using the Cambrian Jacobsville sandstone. They also used basalt down here. There's up there. All right. Now, we're going to look back at our map again. Remember, this was the Cambrian sandstone. Do people see a bullseye pattern here? We're starting to see a bullseye, okay? This is called the Michigan Basin. And we're going to be looking at this Michigan Basin. I liken it to a stack of, let's say, cereal bowls nested inside one another. Now, if you stack cereal bowls in time, like this, one, and put one inside it, one inside it, one inside it, one inside it. The oldest, or shall we say the first cereal bowl down, is on the outside, if you're looking down. And then the next oldest is slightly inside, the next one inside, inside. If you look at the map here, this is what's happening. Remember, I told you early on that older is towards the bottom. So let's just look at this. For example, Ordovician here is here. That means we should get younger as we go to the center, or the next cereal bowl up. Younger, younger, younger. That's called the Michigan Basin, okay? This is all bedrock. This is not what we have out in the yard here, all right? All right. So we got to drive a little bit. And we're going to drive over to Tequamanon Falls. We've gotten younger here. We are now technically in the Michigan Basin, not in the Precambrian, which we talked about, which is over to the west. But we're still at, 490 million. And this is called the Ordovician. Now, the Ordovician is made up of limestones and dolomites. You can think of dolomite as a dirty limestone. It's a limestone that has magnesium and calcium in it, not just calcium carbonate, like chalk, right? But it's calcium magnesium carbonate. So here we are. We're going to be down here. We're going to look at the Ordovician and then the Silurian. Like I said, most of these are carbonates, calcium carbonate. Same thing as Tums, right? That's calcium carbonate. This would be calcium carbonate and calcium magnesium carbonate, what these are made of. Well, there's Tequamanon Falls. Tequamanon Falls, beautiful, where the Tequamanon River falls over these more resistant limestones. So we have the erosional process going on at the surface. And this is a good chance for me to go back to my heat analogy, okay? I said that everything we see on the planet is the Earth trying to cool off. That's true. But we also, and we call that the heat engine, the internal heat engine, okay? So when the planet was formed, very hot, we have radioactive decay, which generates heat. And the planet is doing this, trying to get rid of this heat. Call it a heat engine, an internal heat engine. But we also have an external heat engine, the sun. And the fact that the planet is warmed differentially, we have more heat in one place, less heat in another place on the surface, means that heat always flows from the warm body to the cold body. And we have erosional processes going on. And those atmospheric processes are always working to wear down the surface, okay, to smooth the surface out. Now, so what we have is waterfalls occurring over resistant layers. We have a sandstone down here that's more easily eroded, and then we have this limestone that is more resistant, so we get waterfalls. And this is true throughout the UP. Now, that bit of rock material stretches all the way from Door County through the Garden Peninsula, around Tobermory, all the way down through Ontario over to Niagara Falls, okay? And that's the escarpment you had mentioned. So what do we have? We've got a little bit of a falls over here, right? Niagara Falls. And we have Tequamanon Falls, and we have Door County. These are all part of the same geologic period. These limestones, which are resistant, they'll form cliffs, they'll form waterfalls, and they're in this arch that moves around Michigan. Now, what was it like? We talk about these limestones. What was the Earth like at that time? Different, for sure. Very different. So here is a paleogeographic rendering. So paleogeographic, ancient geography rendering from the Middle Ordovician about 450 million years ago. Here's North America right here. It's called Laurentia, and it's equatorial. All right, much different than where we're at today. So it was equatorial, warm temperatures, shallow, warm seas that will deposit a lot of calcium carbonate. Why warm seas? What does that have to do with it? Well, just think back to some basics that you know. Maybe this morning you recognize that you have a scale on your coffee maker. Right? We have to descale our coffee makers once in a while. Why? Because calcium carbonate is less soluble in warm water than it is in cold water. So you can put more calcium carbonate into cold water than you can warm water. So you have, let's say, some hard water. You make your coffee. What happens? The water heats up. That calcium carbonate's less soluble. It precipitates. So we get these. Now let's ramp this up to a huge global scale. We're precipitating out calcium carbonate because we have warm, shallow seas. All right? Okay. Maybe they look like that. That actually looks quite nice. All right. So here is a cross-section of the Michigan Basin. Remember, I showed a cross-section in the Keweenaw as well. Here is a cross-section of the Michigan Basin. It shows these materials sagging down into a basin under their weight, pushing into the lower crust and the upper mantle. And you'll see that we have the older rocks on the outside and then the younger rocks towards the center. There's a bedrock geology map, another one of the Michigan Basin, and you see this bullseye pattern. Of course, the Michigan Basin does go outside of Michigan, so over into Wisconsin. All right, well, Tequamanon Falls, great place. Anyone who's camped there, it's a beautiful park, but the black flies, if you get it at the wrong time, are not nice, okay? I've been told that as long as it's past July 4th, you're okay. But before July 4th, not okay. I've been there on July 4th weekend, it wasn't okay. Why the black flies? The black flies love clean flowing water, right? So one of the downsides of having clean, fresh, pristine water is you get the black flies. All right, so let's drive down to St. Ignace. We're going to go buy limestones, okay? We're going to go buy more limestones on our way. We're going to get down to the Straits. That thing might be hauling iron ore, who knows? Now we're going to look at the Silurian, all right? The Silurian, we're getting a little younger. This Silurian limestone bedrock right around St. Ignace and around those beautiful beaches along Highway 2. You know, when you head west from the Straits, you go right along the lake and you see these steps of limestone on the beach. Beautiful place. So here we are. Now we're right here in the Silurian. We're moving up in time. Huh. What is that? Some people might recognize it. Yeah, it is. It is. It's a limestone quarry. It's the same limestone that's at the Straits of Mackinac. Yes. Yes. So this on 294, you cross it on 294 on your way to Chicago. This is the same rock that's up at the Straits. Okay. It's the same limestone, but because of that basinal effect, we pick it up down at the Indiana-Illinois border as well. And that quarry is a pretty famous one for anybody who's driven around the Chicago area for a number of years. All right. Now, again, I just keep hitting this geologic map of Michigan to show you what we're talking about. And A to B is the cross-section line right here. So if you would slice down from A to B, from northwest to southeast, That's what the bedrocks would look like. Now, we have fossiliferous limestones now as well. These are called crinoids. They're little stems of sea creatures. You see a nice big outcrop on your walk around Mackinac Island. Now, I want to point something out to you here, which we'll pick up later. Notice the porous nature of this. A lot of holes, a lot of cavities in this, okay? These were not formed just because it's at the surface, okay? This is how this looks in the subsurface as well, all right? So just keep that in mind. We are going to go over to Alpena now. So we're making good progress. 417 million years. We're going to go over to Alpena, Michigan. Again, here's our cross section. We're going to be in the Devonian now. So that's named after Devonshire, England. All right. Like I said, we have a lot of names that come over from Great Britain. And so now we're in the Devonian period, another limestone period. The basinal effect. We pick it up here, here, and there. There's a picture. Notice the holes in the limestone. A lot of limestone mining at Lafarge quarries, right? In Rogers City and Alpena, another big economic boom for Michigan. Limestone, you need limestone to make concrete, right? Without concrete, you have a difficult time having a industrialized and modern infrastructure. So let's just step back, 30,000 foot level for a second. We have, if you think back of the history of Michigan and the geologic history of Michigan, we have copper, wire, we have iron ore, steel, we have limestone, concrete. And Michigan was really coming on the scene right, just before the Industrial Revolution in this country, just before the Civil War. We were founded, 1837 when we became a state. So you can see where it fit in to the history of America and the history of America's Industrial Revolution. Horace Greeley's comment, "Go west, young man," was referring to the Keweenaw, wasn't referring to Wyoming or Colorado. So we put this in context. Cement is a, you can't do cement without limestone. Again, remember this little quip I said in the extractive industries: if you can't grow it, you got to mine it, okay, or pump it. Students on a field trip in the Lafarge quarry. One thing about geology is you have to get out and see the rocks, okay? You have to get out and put your nose on the rocks, as we say. We have a lot of paleontological evidence from these limestones as well. Things called stromatolites. Some of the earliest indicators of life on the planet are in these limestones. Colonial corals. All right, well, Alpena, nice place. We're going to drive to the west towards Kalkaska, Michigan. 380 million years old in Kalkaska. We are going to be right down here in the Middle Devonian. This is yet another column of Michigan. This has the age, the outcrops. This is a nice one. We have geologic time, era, period, and epoch. We have outcrop nomenclature. Very interesting names. Names are typically, there's a naming system. Most often they refer to some type locality where the rock was first described. Okay, so you see a lot of town names or river names or region names and things like that. Coldwater Shale, Coldwater, Michigan. Thunder Bay limestone, right? Things like that. Now, we also have on this column lithologic indicator. Lithology means rock type. And then we have a legend over here of the different rocks. You know, you could spend a lot of time just staring at geologic maps. It's really fun. Okay, believe me. Get a geologic map and stare at it. There's so much information there. All right. Aha. What about those limestones near Kalkaska? Well, there is a formation called the Niagaran Reef Trend in the Kalkaska region that stretches across the upper part of the Lower Peninsula that's been very productive in oil and natural gas. Now, that shows you a map of the outcropping in that area, Kalkaska area. And these are buried reefs. Now, right here is a picture of Great Barrier Reef. The reefs that were formed at that time were very similar. Now, let's talk for a second about a reef. If you think of all the National Geographics and the NOVAs and things like that that you've seen, when they have scuba people go down and they scuba dive along the reef, what is something that is characteristic of the reef? Coral, right? Coral, fish, diversity of life, a lot of strange things living in holes, right? And, you know, people doing things, sticking their hands in and stuff I wouldn't do, right? Do you remember the picture I showed you of the limestone on Mackinac Island with all of those holes in it? A reef makes a fantastic place to store hydrocarbons like natural gas and crude oil. All right. And so reef reservoirs are very common. West Texas, you might have heard of West Texas before. That's a lot of reef reservoirs, okay? West Texas Intermediate is the crude oil from there. So we have produced a lot of crude oil from reef environments. All right. They look like that. Beautiful. So let's talk about this. We have to talk about petroleum. In a nutshell, you have to have 4 things to have a petroleum accumulation. You have to have a source rock. Maybe some of you have thought of, where does crude oil and natural gas come from anyway? Well, it comes from, it's a fossil fuel. It comes from the decaying remains of ocean life, of algal and planktonic organisms that die and sink to the bottom of the ocean. And the sediments down there are usually organic rich shales. And then what happens is, as that gets buried, that organic material gets transformed into something called kerogen, which then gets transformed into crude oil and natural gas, all right, as it heats up. And so what do you need? You need 4 things for an oil accumulation. You need a source, like a shale, marine shale, source rock. You need to have some way for it to move. Because what happens? Think about this. If I have this organic petroleum product in a shale, and the organic material is forming this hydrocarbon, what's it going to do compared to its surroundings? It's going to be less dense, right? We know that oil floats on top of water. So what happens is those little bits of petroleum product have to move, and they're going to want to move up. So if we're going to have a petroleum accumulation, we also have to have a pathway for them to migrate. So you have your source rock, you have your migration pathway. Okay, those are 2 of the 4 things we need. imagine this in your mind. Deep within the earth, you've got organics. They're forming petroleum products. Those petroleum products are lighter than the surroundings. They start rising up. They have to have a place to go. They find a migration pathway. Then we have to put them somewhere. Let's put them in a reef. Okay, this is a very cartoonish looking slide. We put them in a reef. And then we have to stop them from moving because they're still going to move. So now they're accumulating in these holes of this reef. We have to bring something over the top called a seal to keep them there. And that seal will be more marine shales that come in, more sediments that come in and come down and bury them. All right. So those are our four things: a source, a migration pathway, a reservoir rock, a place to put it, and a seal. Then you have what's called a trap. And then you have something that you can drill into, if you can find it, and extract the petroleum from. Okay. Now, that was just a flyover of Petroleum Geology 101. Okay. So you passed that. Now, here is a reef trap. This is what we're talking about when we talk about the Kalkaska area. Some of you might be really interested and say, wow, this is kind of cool. What's this right here? Well, that's a salt dome. Okay. That's the kind of traps we have in the Gulf Coast of the US. A lot of salt dome production. We have other types of traps as well. So right there, that reef trap is what we're talking about in Michigan. Antrim shale. Well, the Antrim shale, because I said it's a shale, it could be, right? It could be a seal. It could be a source. It could be both. Well, what if we had the technology to actually go to the source? So we didn't have to just find where it had migrated to, but we could drill into the source rock itself and extract the hydrocarbons. Well, the Antrim shale is one of those situations. Here it is in our column right here. That's what it looks like. Wow, that doesn't look like it's got a lot of space in it. Well, it does. If we could go in and actually break apart that shale and get the petroleum right at its source, that would be a revolutionary way of extracting crude oil. And in fact, we do that. And that's the hydrofracking story. Okay. So what happens with the hydrofracking story is two components. One, we've learned how to drill horizontally. So we don't have to just drill vertically, but we can actually turn that drill bit sideways and drill along the formation. So you think about it, if you've got this horizontal formation, if you can only access it where you cross it, that's pretty limited. But if you can go into it, turn, make a 90-degree turn and drill across it, you have much more exposure. And then we have ways to break it apart with fracking fluids and get those hydrocarbons to come out. Fracking has, revolutionized the oil and gas industry. Now, are there challenges with it? Yes. If it's done poorly, there are risks in it, risks to groundwater potentially. And we've heard of some of these. Overall, fracking has been a very advantageous way to do oil and gas exploration. Does it need to be regulated? Absolutely. Do we have to bring mistakes and errors down to close to zero as possible? Absolutely. But it has been a game changer in oil and gas exploration. Now, just before we take questions and break, I want to just show you that Michigan has been a very productive state in terms of hydrocarbons. So this just goes up to 2005. Total cumulative production in Michigan, 1,200 million barrels of oil, 5.8 trillion cubic feet of gas. That's a lot. I think we're about 18th maybe in the country, 18th in the nation for total production. But back in the 50s and 60s, there was a lot of Amoco and shell production up in that area. And there's still some activity up there. Here, I bring this up. This is from the Energy Information Administration. Thousands of barrels, Michigan field production of crude oil. And you see how it's declining, but declining like this up until the present time. But historically, we produced quite a bit from those limestones. Here's natural gas withdrawals, same source here I'm using. You saw we had a spike there in the early 2000s, and now we're down again. Okay, before we head over to Charlevoix, we can probably drive over there over our lunch period. Any questions right now that I can answer? Yeah, we've got a few questions. Yes, sir.
This question relates to something you said a while ago about copper mining in the Upper Peninsula.
Yeah.
You mentioned that it wasn't economically feasible to do the shaft mining, and I'm just curious as to whether mining companies can do other ways of mining in the Upper Peninsula, or is it limited by the geology or environmental concerns? They don't do a more economic, viable way of mining.
Yeah, it's a great question. Let me answer it in a few ways. We know we can't go any deeper with those shafts because of the water problem. You know, to pump water is super expensive, right? Some of these shafts are almost a mile deep. And so that's a lot to do. So that piece can't be done. Sometimes they will, if the price of copper bounces, they will reopen some shallow regions. They will also go into what are called the poor rock piles up there and extract copper, because back in the heyday, you know, they were throwing away native copper into the poor rock piles because it wasn't big enough to stamp out, right? So that kind of reclamation work can go on. But, you know, economically, the sulfides and the carbonates and things like that from the Western open pit mines just can't, the shafts can't compete. And also there's a safety issue. The open pit mines are much safer when you're out in the open than in the underground, for sure.
And one other question. I heard somebody talk about electric vehicles and a need for cobalt that could be mined in the Upper Peninsula. Do you have any thoughts on that? Whether cobalt?
Yeah, that's a very interesting topic. And that's the whole rare earth element mining topic, which is a global question. And maybe, I tell you what, maybe if we have time, I'll get into rare earth mining and the challenge we're facing with rare earth mining globally and the geopolitics of it. It's very serious. Okay, so we can talk about that. Yes, sir.
So many of these rocks were formed at the bottom of a warm water, a sea. And did these tend to be regional seas, like a sea that would cover the Midwest, or was it a more generalized sea that would be connected to what is now the Atlantic or the Gulf?
Yeah. These were, sometimes they were regional seas, something that would look like Hudson Bay. Sometimes. At this point, they were much more globally, you know, in scale. Now, we have to realize that these continents are near equatorial at this point, and a lot of them are fragments of continents. We will see as we go through geologic history that these continents came together into a large supercontinent called Pangaea. And then about 200 million years ago, that broke up again. So we were seeing the continents come together, microcontinents coming together into larger continents, and then at points, the larger continents breaking out again. Okay, so at this time, these seas are pretty extensive. All right.
I have one other question. On the fracking, there's a certain type of sand that needs to be mined to be used in the fracking process. And I recall some environmentalists being concerned about the areas where the sand mining was occurring. Can you say anything about that?
Yeah, I will say something more about it when we get to that part of the geologic history. We're going to get to the Pleistocene, which is all the unconsolidated materials, and we'll talk about sand mining in Michigan. That's a great question.
I have a question about fracking, about how deep do they go for fracking and does it cause earthquakes?
Yeah, that's a great question. And the U.S. Geological Survey has been working a lot on this in Kansas, where there's a lot of fracking. Now, you can, let me answer the question a little differently. You know, the industry routinely drills at 25,000 feet in the Gulf Coast, 28,000 feet. Offshore can be 32,000 feet. That's deep, okay? And we have to respect the technology and the success. And let me just say this. Next time you're in an airplane and you're flying and you're in a window seat and the flight attendant says, well, now we've reached 10,000 feet. You can turn on your phone or whatever you do. Look out the window. That's 10,000 feet. We're drilling routinely at 30,000 feet. And that's with a 5 1/8 inch bit. And we're finding a reservoir at that depth. So it's amazing. Okay. Now back to fracking. We can frack as deep as we can pump the fluid down there. And so something about the fracking fluids, they're not just water. They have to be made more dense so the pressure exerted on the rocks is enough to break them. But that's not the whole story with fracking. Once we crack them open and make space, we have to make sure that we keep those cracks open. And that is the whole realm of proppants. So beads, plastic beads, etc., are put into that fluid. So once that fracking fluid is removed, these little beads prop the holes open so the hydrocarbons can flow. And there's a whole industry on disposing of those frac fluids then. And yeah, it's a big job. Yeah. Yes, sir.
Basalt.
Yeah.
So if I handed you a sample of basalt from the Western UP and then another sample of basalt from the other side of the planet, would you be able to tell me where those came from? Or would you even be able to tell me that they're different?
Okay, that's great. At first, when you handed it to me, what I would look at is I would look at the physical texture of it. If it was very frothy and looked like Swiss cheese, I would know that it came from something subaerial. In other words, it was erupted out under air, bubbles could form, and it chilled like that. If it was dense solid, it could either be submarine or it could be subaerial, but in the middle of the flow. Again, if it came out and it looked like rope, I could tell you that maybe it came from Hawaii or Southwest United States. It's called pahoehoe. It's a ropey flow. If it came out blocky and looked like chunks, it means that the slope on which it was erupted was steeper. It could not form ropes, but it broke as it crumbled. So I could tell you certain aspects of it. Now, to tell you exactly where it came from, I would need chemical analysis and even isotopic analysis. It's possible. It's possible. Now, not, 40 East 12th Street, but I mean, I could say this is from Iceland, Yeah, right. Yes, sir.
The bowl analogy of the different layers
Yeah.
is very fascinating. Since all this was equatorial in that proto North America thing
Right.
at the equator, are there other clearly identifiable bowl analogies, other places in North America?
Yeah, there are other basins. This is probably the
Basins,
biggest
yeah.
basin. There are, around the world, there are basins as well. There are also domes. So think of now taking your stack and turning it upside down, right? Now the oldest is going to be in the center. If you take your stack of cereal bowls and tip it upside down or stack them upside down, the oldest would be on top, but the oldest would be in the center as you look down. As you went out, you saw those rims of the bowl, they would be getting younger, just the opposite of the basin. Oh, I would say probably Western United States is where I think of a dome. Yeah.
you know, we've looked at all these maps and we see the bowl and all these things, but there's the big white space, which is Lake Michigan and Lake Superior. Do people do geology under these? And, you know, they offshore or whatever, is there stuff that we're gonna be getting out of the ground underneath the water?
Oh, okay, so this is a big question, right? I'm gonna just take it apart a little bit. We're gonna get to the Great Lakes and the formation of the Great Lakes. That's young stuff. These are young out here, okay? We're gonna get to that. Now, your question of whether we can drill offshore Michigan, we can't. I mean, we can't do that, okay? And so it's not even on the table. There has been some talk. But I think that's probably fiction. I do not see rigs in Lake Michigan. Yeah. Anything else before we break?
And
Oh, got one more question here. Yes, sir.
hasn't there been some talk of angle drilling where they can be on shore but drill under the basin?
Yep, there's been talk of that.
And
Yeah.
they could-
I don't know where that sits right now, but there was talk.
Just one comment, my son was a chemical engineer and he worked for a company that made the fracking fluids. And they built plants wherever they're doing the fracking. But they also, when they're reclaiming the fluids, we all have plastic pipes in our houses and everything. They take the plastics out of the fluid and to make pipe. So the PVC pipe that you're using in your houses and stuff most likely comes from some fracking plant that's changing the fluids into pipe.
Great.
Okay,
Yeah.
let's take our break. If
Okay,
You want
great.
one
We'll
more?
see you this
Yeah.
afternoon.
Yeah, come back at 1 and let's give John a big round of thanks.
Thank you.